Alright guys, welcome back to another tutorial, and this time we're covering, what is this, tutorial number 2 in Unit 3, Osmosis, Diffusion, and Cellular Transport. Alright, so I'm going to go ahead and start you guys off as always on page 4. Oh, nope, just kidding. So page 4 is a lesson activity, feel free to go ahead and start with that, but I'm going to go ahead and go to page 5 now. Alright, so cell membrane, pretty simply. What we're going to cover now is that semi-permeable cell membrane that I mentioned in the last tutorial. Let's go in a little bit more detail and explain what it is. So every time you see a cell, you see a nucleus. You've got the endoplasmic reticulum, and it's shaped all kinds of funny and that kind of thing. And then you've got Golgi bodies or whatever, and ribosomes, whatever else, all sorts of things. But you always see it inside of this sac, and this is what we're talking about. This cell membrane. All right, this outside part is what we're talking about this time. And the idea is not everything is allowed to go through it. It actually has a semi-permeable structure. So what happens is that you have two parts of these little things. All right, look kind of like that. But the idea is inside of the cell membrane. So on the middle of this stuff, you've got these things with these heads pointing on the outside and the inside. All right, so you've got these little cell membranes. These heads are called hydrophilic heads. And these things here are called hydrophobic tails. This desk shakes more than I'm used to, but that's okay. It ought to still work. So hydrophilic heads and hydrophobic tails. And here is what you have to know. Hydro. You guys have probably heard about this. God knows what. Hydroponic systems, hydro, I don't know, whatever else. Hydro just means water, like a fire hydrant. All right, so this is water. And then you guys have probably heard of phobias or phobic, right? Like people that are claustrophobic or arachnophobic or, acrophobic, whatever else. This just means scared of. Scared of, or they don't like it. So basically these tails hide on the inside of the cell in the middle, okay? So they hide in the middle of the membrane, and technically there are a bunch of these. I'm not going to draw, oh crap. I'm not going to draw too many of these because whatever. But these tails do not like the water. They are scared of the water. Hydrophilic, if you had to guess, so I told you guys we learn things in doubles. This one means scared of, so this one means they probably really like it. Alright? So the hydrophilic heads like water. Alright? And that's why you have the tails on the inside of the membrane and heads on the outside. So the idea is this. Between these heads and tails, it's hard to get through them. There are not always pathways. And I drew them kind of badly, but the idea is that they're actually pretty close together. So like the tails are not necessarily touching, but the heads are certainly touching. Alright, so let's put a bunch of, there you go, like that. Whatever. Pretend there are lines between them. But to get through these heads is a little bit difficult. There are certain things that go through really, really easily, like oils and dyes. So if you think about this, if you put oil all over your skin, it's really hard to wash off. That's for a couple of reasons, but it's hard to wash off all that oil. Lotion works in that same way. So like when you put lotion on your skin, the oil gets absorbed a lot quicker. Waters are absorbed pretty quickly through the skin. Dyes. So if you've ever used like I don't know, red food coloring or hair dye, you can easily stain your skin that way just because it happens to move through these membranes really easily. On the other hand, salts like like table salt, if you pour table salt on your arm, it's not like you just suddenly start absorbing salt. It doesn't generally work like that. So some molecules, some substances are much harder to diffuse through here than other molecules. And we're going to talk about what diffusion is, and I think that's on the next page. So let me go ahead and go on to the next page. Okay, so they're going to talk about the fluid mosaic model here. We'll talk about diffusion later, but I'm going to talk about the actual structure of how the cell membrane is. So I gave you all these little circles and whatnot, right? So all these little circles with lines attached to them and that kind of thing. But if you look on page 6 of your tutorial, you'll see a model that they've drawn. And you'll notice a bunch of little things that are stuck in there. So there are little like wiry looking things, and this kind of protein, and then they have carbohydrates on here. Just like that. And they have big proteins that show up in the middle of this. So here's like a protein. It's just a bigger one, I guess. And then, a couple more little heads and tails. And then they've got these proteins that look kind of like that or something. Alright, so here's the idea. These proteins, all these proteins, are like your fingerprints. Alright, so everybody has their own individual fingerprint, like your fingerprints don't match mine, mine don't match yours, etc., etc. These proteins are unique to every single cell. So that's the first thing to remember. These proteins are how other cells can tell what they are. So if one cell bumps into this cell here, it'll know that this cell is a, I don't know, skin cell or whatever else it might be, just because of how its proteins are set up. It's just like a fingerprint. Alright? So the proteins are a big deal in determining what kind of cell you're dealing with. Further, these carbohydrates are used for, and this is going to be a really bad drawing. I highly recommend that you guys just Google a semi-permeable membrane, and it will give you a much better picture than what I've drawn here. But anyway, brain, what the heck? Membrane, sorry. Got lost in thought. Anyway, these carbohydrates are for communication, alright? So C for communication. So when you're remembering all of this, the proteins are for identification and for transferring things through. So like things that don't get in your body really easily, like salt, can go through these proteins, alright? And they'll travel all the way through. It works like a tunnel, alright? So proteins for identification and they work as tunnels. Carbohydrates are for communication, and then the heads protect the inside from water. So like they like water, water hangs out around them, but water can't just fly right through this. It has to go through some channels and whatnot. And then the tails don't like them. So these tails, they don't like the water, they push the water back out, essentially. So if water tries to go through here, it just pushes it back out. So water has to go through something like this, like a protein. Alright, so let's go ahead, and I think that's it. This is a picture. Oh, yeah, and we've already talked about phospholipids. By the way, if you guys ever see the word phospholipid, they're just talking about these things. The hydrophilic and hydrophobic heads and tails, those are phospholipids. They're fats. Alright. Phosphorus heads. Phosphorus heads, phosphorus, whatever. And then lipid tails. So remember, lipids are going to be our fats. And just remember that oils don't mix with water. Like if you mix water and oil, it'll always separate out. The oil will normally be on the bottom. So lipids don't like water. That's why they're on the inside of this, okay? They push water away. Phosphorus, on the other hand, actually quite likes water. So let's see. So we've talked about the phospholipids. That covers page 7. Page 8. All right, so they're going to talk about two types of proteins now. So let's talk about proteins in the membrane, because there are actually two kinds of proteins in here. There are going to be integral proteins and peripheral proteins. Peripheral. Okay, so integral means inside. All right, integral just means inside, so it's inside. Periphery is your outside, so it's like your peripheral vision. It's your vision outside to the left and right of your eyes, right? So integral is inside, peripheral is outside, essentially, or out there. So in your membrane that I drew earlier on, you notice that I have this one that's chilling here, and I have one that's going all the way through and whatnot. Peripheral proteins are going to sit on the outside. They don't have to sit right in there. That's actually more of an integral protein. So hold on. Let me draw you another one. That would be me doing something like this. And now there's a protein out here. All right. So that right there would be a peripheral protein. So these are outside of the membrane. All right. Membrane. And these are mainly for identification. That's their general job. The ones on the inside, however, are for transfer. They're for transfer. Let's see. Let's see. That's really it. And then they can. They're also for identification. So these are for ID. These are also for ID. But the idea is that integral proteins are mostly those tunnels. They're for transferring stuff, or maybe this thing, so it's for transferring again. They're moving things from here to here. Who knows? But the idea is they're for moving things across. These ones on the surface are mostly for identification. Okay, so peripheral versus integral proteins. Go ahead and go on to page 9, where they're talking about, okay, homeostasis. So here the word comes up again, that word that I keep mentioning to you guys. Homeostasis is that idea of balance, okay? So the cells have to have a balance. Every cell has a certain type of squishiness. So your hand has a certain type of squishiness, right? So if if for whatever reason you eat too much of something or too little of something, you end up with different levels of squishiness. If you've ever eaten a whole lot of salt, so if you like cover your digestive system with salt, um, you'll end up seeing changes in your skin. You should see it be a little bit puffier. Your faces will often get puffier if you've been eating a whole lot of salt, just because it has to balance out that salt intake with more water. So you have more water retention when you eat more salt. Retention, by the way, means to keep something. So water retention is how much water you keep in your body. All right. So let's talk about the types of homeostasis, or rather the things that affect homeostasis. There are specific words for them. All right. Cellular diffusion. Diffusion. This is probably more of a vocab word than it is a bio word, but diffusion literally just means spreading. All right. So this is spreading or moving. Um, And the idea is everything that we have in our body is going to spread or move. Everything we have anywhere is going to spread or move. The easiest representation of this is if I put like 80 of you guys in one of our portables or one of our rooms or something like that, you're probably going to get kind of uncomfortable. Some of you guys are going to leave. That leaving motion is called diffusion. So that is diffusion because you're moving from so you move from higher concentration to lower concentration. And this is how you're going to hear it, but to simplify that, it's just if you're in a crowded room, some people will move to a less crowded room. I know parties aren't always like that, but there are always those people that move from a higher concentration to a lower concentration because it gets too packed. So you take the easiest way out. Okay? So that is what diffusion is. It literally is just moving from somewhere where it's crowded to somewhere where it's less crowded. All right? Uh, And on page 10, they're going to show you how things move in and out of the cell membrane, like oxygen and water and CO2. They show that they move in and out depending on what we need. All right, so page 11 is going to cover the two types of diffusion. Let's talk about those two types of diffusion. Let's keep this kind of at the top of the page. Sort of. There we go. Okay, so there's diffusion, and there are two types. There's going to be simple diffusion, and simple with an M, and facilitated. To facilitate something just means to help it, alright? So this is to help. Basically, there's diffusion of higher to lower. So like nobody needs to help you leave a room um, if it's super, super crowded. You can just leave, right? But facilitated would be like if you were injured in a room and the ambulance came and they facilitated or they helped you out of the room. That would be different. This is essentially done by proteins. So this is diffusion across proteins. Diffusion across proteins. Now this doesn't require any extra energy. It just means that somebody's going to help you across because it happens to be there. It's kind of like uh, this is essentially a doorway. So you can't really just simply diffuse through a wall. This is higher to lower, higher to lower. Okay? So you cannot just move through a wall. So you have to have a doorway. These proteins act like doorways. Alright, so these proteins are those, just like up here, they're these things. These pathways that I mentioned earlier, that is facilitated diffusion. Alright? So that is the difference between simple and facilitated. One has proteins or something else. It doesn't have to be a protein, but 9 times out of 10 it's a protein. Well, 99 times out of 100 it's actually a protein. But the idea is it's diffusion across using protein. Okay? Both of these don't require energy. So these are no energy. So if I use the word diffusion, just remember it's natural. It doesn't require energy. It's just people walking through a door, or it's people, I guess, walking in and out of a house. That's kind of a bad example because it makes it seem like they're both the same thing. But just remember this one has to do with proteins, this one does not. Alright, so that's simple versus facilitated diffusion. So let's go ahead and move on to page 12. And now they're talking about osmosis. Osmosis is that special one, okay? So osmosis is diffusion. Here we go. Oh, you guys can't see that. Osmosis. And osmosis is diffusion of water. That's really all it is. So basically, it's where if you have a lot of water on the outside of your body and not a whole lot of water in, well, let's say you're just in water, right? You put your hand in a cup or you sit in a bath or pool or whatever for just way too long. What happens is that your hand gets all shrivelly and bloated and stuff, right? Because you've absorbed all that water, so your skin gets all unusual and wrinkly. So that's caused by osmosis. Naturally, the water on the outside of your body wants to enter in, and your body wants it to enter in because you have less than that. So by simple diffusion, we have osmosis. All right, diffusion of water from higher concentrations to lower concentrations. All right, always moves from higher to lower. Uh, Now let's talk about osmosis and how they do it. I think they're gonna do it here. Good, excellent. So remember that everything moves from higher to lower. So if there's more of this on the outside, there's whatever on the inside. What we want to talk about is I want to talk about hypertonic, hypotonic, and isotonic solutions. There we go. Okay, so on page 15, sorry, I had to skip around to figure out where they're talking about it. It follows to do osmosis and then teach us next thing. It's actually really, really useful. All right, so there are three kinds of solutions in osmosis. So imagine this is going to be like your skin, okay? It's going to be your skin, and you're going to put it in things because your cells are all like this, and things move in and out of the membrane. So there are three types of solutions. One's called isotonic. All right. So what this means is that you have your cell, right here is your cell, and then you have your cup of water, or whatever it is. And in this solution, it's isotonic. That means let's say the cell has 3 sodiums in it. 3% sodium, okay? And the water out here has 3% sodium. That means that there's going to be a net movement of 0. Net movement of 0. What that means is that water and whatnot is going to enter the cell at the same rate that it's going to exit. So they're going to move out and they're going to move in at the same exact rate, giving you a net movement of 0. This is kind of like if you have 2 doors, one's an indoor, one's an outdoor, and you're having a party, right? And 3 people enter your house every hour. 3 people leave your house every hour. Your people are changing. The stuff inside is changing. So stuff is still moving around. People are still coming in and out, but they're coming at an equal rate. So your party's not getting more or less um, busy. It's always going to be the same number of people. All right. So that's an isotonic situation. All right. Might remember this from isosceles triangles. So isosceles triangles have 2 sides that are absolutely equal, while isotonic situations have 2 membranes or 2 concentrations that are exactly equal, causes a net movement of 0. They're just going to move in and out at the same rate. All right, let's talk about hypertonic now. Hypertonic. So what hypertonic means is that the water on the outside is going to be heavily saturated. And remember what saturated means is filled up with stuff, right? So here's my cell. Let's say it still has 3%, but the outside's going to have somewhere like 90%, like a really massive amount of solute. So basically, you've got a whole lot of salt. You've got really salty water. Okay, so this is just barely salty. This is really salty. All right, super salty. And what's going to happen is that water is going to move out of the cell. All right, water moves out, because the outside of the water is way more saturated than the inside of your cell. So it tries to even out. The idea is that they both want to get to like 50-50. They want to get to isotonic, all right? So they want to be equal. So they're just going to leave this until this percentage goes down to whatever this one is. So as the water leaves here, this is going to keep rising. It's going to move up to like 4, 5, 6, 7%. And this one's going to drop to like 89, 88, 87. The idea is they want to be balanced. They want the same number like an isotonic state. This is the natural state. After everything's settled, it will get here, and they're just going to go in and out at the same rate. Here in a hypertonic situation, it's going to leave like crazy until they match up. But the problem is that this thing shrivels. Your cell will shrivel here like crazy, and it'll probably die. So this is why we don't do too well sitting in salt water for forever, because it causes you to shrivel and die. All right. This is why plants, if you feed them salt water, they will shrivel and die, because it literally dehydrates a plant. It pulls all the water from the plant. All right. So a hypotonic is going to be the exact opposite. So we have, I told you, we learn things in pairs. So like this is the word for balance in liquids and this kind of thing, solutions. So this is isotonic, that's balance or homeostasis. Hypertonic is the outside is way more concentrated than the inside, so water leaves. Hypertonic, water leaves. Hypotonic, so let's draw another little beaker. This cell I'm going to give more concentration just because it'll make for my example to be easier. So 90% and this is 3%. So now this is not salty at all, but the inside of your cell, inside of cell, is too salty. All right, too salty. That is not good. All right, so you have to drink a lot of water when you eat a lot of salt. So you drink a massive amount of water, right? So there's like this situation. The idea is that the water will enter the cell because you drink all that water, your body will retain more. This I told you guys earlier. Let's say you had a whole lot of salt. You've been eating just a lot of salt. Your body gets a little puffy. Your face normally gets kind of bloated, a little bit puffy. And the reason for that is because all the water that you're drinking when you're eating all that salt, all that water is entering your cells because your body's not sure how to balance it out otherwise. The idea is that this will slowly drop and this will slowly rise. So water moves in. And now the problem is when you don't have a whole lot of salt in your body, or even if you do have a lot of salt, your cells get puffy. We just talked about that, right? Your face looks a little bigger. If you put this thing and leave it in a hypertonic situation for too long, your cells will absorb too much water and they will start to burst or they will start to pop. This is called lysing. Oh, you guys can't see that. This is called lysing, okay? L-Y-S-E. It means to pop or to blow up. So as water moves in, this is, like I said again, your face gets puffy. It could get too puffy and technically pop. Now, it's not going to happen, but, you know, theoretically, your individual cells can pop. Your whole head's not going to pop, but your individual cells can pop and die. Okay, so just to review these three, and this is important, it's going to show up on your mastery test a lot, I'm sure. Isotonic is where they're equal, net movement of 0, but they are still moving. All right, so stuff is still moving, but the net movement is 0. So please don't confuse that with no movement at all. There's definitely movement, it's just equal on both sides. Hypertonic means that water is going to leave the cell. All right, this is like planting my plant in salty soil and water. Like if I keep feeding my plant salt water, it's gonna die. It's gonna shrivel and die. All right, so this is like a plant with salt water. All right, that's not good. Water is gonna leave. Your plant's gonna dehydrate and wilt. Over on here, the hypotonic. This is like me having, you know, your skin, and you've been eating too much salt, so you retain more water. So water is gonna move into your body, and it's gonna retain better. And then your cells are all gonna get puffy, and they're gonna pop. Okay, so isotonic, hypertonic, hypotonic. Definitely make sure you know the difference between the three. Sorry that was so long, but it's actually a really, really important idea. All right. On page 16, it talks about the factors controlling osmosis and diffusion. Osmosis and diffusion. All right. So those processes that affect osmosis and diffusion are the permeability of the membrane. All right. The membrane, like I said, is highly permeable to certain types of molecules over others. So like water technically shouldn't be something that it's highly permeable to, but because of osmosis, the cell naturally takes in water. It's technically kind of an unusual situation. Like water, we think of water as a very regular thing, but technically because it's a polar molecule, because it has that rate and that charge, it shouldn't so easily cross, but it does. Steepness of the concentration gradient is the second one. So concentration gradient really just means that if I have in my last example, let's see. In my last example, I had like 3% to 90, right? So 3% and 90 are really, really different. That's a massive difference. So it's going to be super easy for water to like leave or water to go into these cells because it's 3% and 90. But if I had made these like 65 and 60, it would have been a much different situation. Now 65 and 60, it's not going to move as fast. So it's less permeable when the balance is pretty equal. All right. But as soon as they're far away, so 3% and 90, this is going to cause a huge difference. That means that things are going to diffuse faster. That actually makes perfect sense because if outside of a party I have 50 people and inside of the party I have 50 people, they're probably not going to move in and out that fast. You know, I might get 3 or 4 people leaving, so I'm going to bring in 3 or 4 people, whatever. But it's not really that big a deal. However, if I have like 3 people in the club and 50 people outside the club, chances are I'm going to pull all 50 in. So the concentration gradient really just means how big is the difference between how packed it is. So if it's not packed inside, super packed outside, you're going to move people in real fast. But if it's kind of packed in both sides, you really don't care. You're just going to kind of move people in slowly. It's going to be whatever. All right. So that is the idea of the steepness of a concentration gradient. Lipid solubility really just means that things that are dissolved by lipids, so dissolved by fats, are going to be absorbed really easily. Good example of this would be, well, salts actually do a pretty good job. What dissolve in fats? Soaps. Soaps dissolve in fat really well. That kind of thing. Not that your body takes in a lot of salt. Um, but yeah. I think garlic, actually. Anybody who eats a lot of garlic, that's good for like weight loss and whatnot. I'm pretty sure that those are very lipid soluble. So your body takes in garlic really easily. And that's why your body, when you eat garlic, smells a lot like garlic. Like it's a really strong smell. Mostly because it's very lipid soluble. Alright? So, and then size, obviously. So smaller molecules like water. Water gets through pretty easily and whatnot. Oxygen, super small, so that gets in really easily. But if you have a giant molecule like C6H12O6, so you know that glucose molecule, glucose is not going to just move. That's sugar, by the way. So if you take like a really basic sugar and you just like spread it over your hand, it's not going to just sink into your hand. It doesn't work like that. But oxygen, all the air around, is going to move in and out of my skin pretty easily. All right. So that is those are the factors affecting osmosis and diffusion. Let's see what else. Oh, and they mentioned a couple more. Surface area, surface area and size are essentially the same thing. Pressure, obviously, if I squeeze this water into the cell, or if I squeeze the cell to get water out, it's going to move faster. So pressure affects it. Temperature also affects it. So normally in a warmer situation, molecules will move in and out a little bit faster. I told you guys higher temperatures generally speed things up. So like with catalysts and enzymes, if you heat it up, it probably affects the rate of the reaction a little bit faster. Same goes for this. Temperature, a little higher temperature makes it a little bit easier for water to go in and out. That's why when it's hot, we sweat so much, and we also absorb water really easily and that kind of thing. That's why you get dehydrated really easily, because water is moving in and out of your skin really fast. So that is temperature. And then charge. So like uncharged particles move really fast. Charged ones do not, because this lipid membrane, where is my notes? Okay, so this lipid membrane has its own charge, okay? So it might be, positive or negative, whatever it is in here. It has its own charge. So if I have, whatever charge, a positive and a positive here, the positives are supposed to be repelled. They're supposed to be pushed away. Remember, like charges repel each other. So if it's positive in here, any positive molecule should be pulled out. That's why I said water, because it's slightly charged, is kind of an unusual situation. Our body needs water, so it has methods for dealing with that and taking in a whole lot of water. But normally, anything charged, anything with a positive or negative charge, would not get through this membrane so easily. All right, so that's a big deal. Let's go ahead and go on to page 18, or, sorry. And now they're going to talk about one more type of transport. So we talked about simple and facilitated diffusion, right? So simple and facilitated diffusion, they don't require energy, it just naturally happens. There's one more type of diffusion that happens. Or rather, I guess it's not called diffusion anymore, but there's one more type of movement of molecules in the cell, and it's going to be called active transport. Active. So this one here is where you're actively getting help to do things, alright? Active transport. So if you think about it, diffusion, simple diffusion is kind of like air just kind of seeping in and out of, you know, in and out of your porch, right? So your porch is screened in, and air just kind of moves in and out as it feels like. So that's simple diffusion. Facilitated diffusion, on the other hand, is like there's a doorway, and now you have to walk through that door. That is facilitated diffusion. Active transport is like I said earlier, and I use this poorly as an example, but it was like the ambulance people or whatever carrying you out. So active transport is where you use ATP, all right, you use energy to move stuff. And this is going to happen for certain kinds of molecules. Most famous example of this is sodium potassium pump, but we'll go over this, I hope, in a little bit. If not, I'll mention it at the end. So active transport uses ATP to move things that shouldn't be moved across. So like I told you earlier, they don't like things that are really big, right? So really big molecules like C6H12O6, the glucose, they're going to move that into the molecule or into the cell by using ATP. That's going to be active transport. Sodium is highly charged. Sodium ions are charged, so they have a hard time getting through. So we're going to use um, a certain type of channel to do that. It's going to be using ATP. All right, so this is going to be using endocytosis and exocytosis. Endocytosis, cytosis. All right, this is going to be the movement of big molecules of molecules, generally large ones, into the cell. All right, into the cell. So this is a type of active transport. Endocytosis, it moves things in. So if one thing moves things in, you guys can probably guess there's another thing that's going to move them out. And we're going to use a word that means out. You guys might remember it starts with an E. We saw it before. It means, or the word is exocytosis. All right. So this is movement of molecules out. All right. Always going to be a balancing effect out of the cell. Now, there are going to be two types of endocytosis, by the way. One is called pinocytosis, and the other one's going to be phagocytosis. Cytosis. All right, both of these spelled with PHs, by the way. Or I'm sorry, this is spelled with PH, by the way. So pinocytosis is just going to be the process of I guess I should say swallowing liquids. So that's when the cell takes in liquids, all right, like water. So this would be like pinocytosis. If the cell were to go out of its way to get some liquid, it would be pinocytosis. On the other hand, phagocytosis, if this one's swallowing liquids, what do you think this one is? It's swallowing foods or solids. All right, so I'm going to write solids, but it's really just like foods and whatnot. This is when the cell reaches for something. Just so you know, this process looks kind of like this. So here's your cell, right? What's going to happen is your cell is going to essentially surround some kind of molecule. So here's some like food bits, right? Here's food bits. And what it's going to do is it's going to open up around these things. And it's going to slowly engulf them. And what's going to happen is you end up with a vacuole inside of your membrane. So you guys remember these vacuoles, right? So that is the entire process. It's just that your cell will surround these little dots, turn it into a little bag, and then eat it. All right, so that's phago and pinocytosis. All right. Exocytosis is, on the other hand, it'll package it from the inside, so that would be like the reverse. So start from here. It starts with it inside, it's going to slowly spit it out, and then spit it all the way out. All right, so that's endo versus exocytosis. I'm hoping they talk about this pump. Okay, cool. So membrane protein pumps. So I told you guys that there are pumps that we use. Some of them are like this, and you can just, some molecules will walk right through them. Others are like this. So I'm going to talk about the sodium potassium pump, and it looks something like this. The idea is it's kind of like an hourglass, sort of. And what happens is, so remember, there are a bunch of little things here, because this is the outside of the cell, so there's a membrane protein just like regular. But the idea is you're going to have some sodium out here, so some Na, I think it's plus, if I'm not mistaken. It is going to be Na plus. All right. Let me make sure about that before I just. Hold on one sec. Yes. Okay. So it is an Na plus. Is it? Okay. Cool. So it is going to be a positive sodium ion, and the idea is this sodium potassium pump is, oh well, I kind of drew this wrong. It's not entirely like an hourglass. Whatever. So what's going to happen is it's going to essentially have sodium on the outside. So here's the outside of the cell, and then this is the inside, obviously. And it's going to have potassium in here, which is also a positive. So the main problem is I can't deal with the concentration gradient in here. Maybe it's positive, so it's repelling all these away. But the idea is this potassium pump is going to open up. It's going to open up like a square. And then the Na is going to enter and the K is going to enter, and then it's going to close essentially, and the potassium is going to go out, the sodium is going to go in. This is a really bad diagram. Feel free to YouTube sodium potassium pump, but the idea is it trades out potassium for sodium, or vice versa, that kind of thing. So it'll trade out its molecules, but it has to open up for that to happen, and then it has to close up again. This potassium or sodium potassium pump does not always run. If you have enough sodium or if you have enough potassium, whatever, it just kind of slows down. If you are in need of one of these things, it'll speed up. But the idea is it's going to use and burn up ATP to exchange these different substances. All right. So that is the sodium potassium pump. That's an idea of active transport. So active transport is just like you saw earlier with um, pinocytosis and phagocytosis. It's with the cell eating things. So that's absolutely going to use active transport. But even more than that, this is probably the more common kind. This one happens all the time in your body. It's just your body slowly moving things in and out by changing the shapes of proteins. So in this case, it changes from like this funnel hourglass shape to like a tube essentially, and then back to this funnel hourglass shape. And it's going to keep opening and closing until enough stuff happens. All right. It looks like there was a video for that on your tutorial on page 19, so feel free to check that out. That might explain it a little better. But it looks like we're done with the chapter, so do make sure that you remember all the different things that we've covered today. The difference between simple and active, or simple and facilitated diffusion. So remember, neither of them use energy, okay? But this one uses proteins. And then active transport, which is the other kind of movement, and this one's going to use ATP. Know the difference between pino and phagocytosis, exocytosis, and endocytosis. Remember osmosis, and definitely know your isotonic, hypertonic, and hypotonic. All right, guys, this mastery test is really, really fair, but it is definitely hard if you don't know the differences between all of your things. So this one's going to be a lot about how you know, or how much you know about each given subject. Feel free to call me or message me if you need any help, but I think that you guys should be good based on just this. Let me know how it goes, and good luck. I'll see you guys next video. All right, bye.